In this video, we're solving problem 14.7.041 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're asked to convert the integral from rectangular coordinates to both spherical and cylindrical coordinates and evaluate the simplest iterated integral. So this is the integral that we're starting with. They give us bounds for z, bounds for y, and bounds for x. Remember how that works. The innermost bounds go with the innermost variable. That second set of bounds, goes with the next variable, and that third set goes with the last variable. This is our integrand, and this is dv in rectangular coordinates. We want to take that and we want to convert to cylindrical coordinates, which are just like polar coordinates, except we've got a z as well. And we also want to convert to spherical coordinates. Now this is what's given to us in WebAssign. We're given lower bounds for z and r and theta, and we're asked to find the appropriate upper bounds given those choices of lower bounds. We also need an integrand that will come from replacing the dv with the appropriate expression and replacing that x with the appropriate expression. And so that will give us an integral in cylindrical coordinates. Now we're going to do the same thing in spherical coordinates. I think we can see, though, that when we convert to spherical coordinates, it is going to be more complicated than it is in cylindrical coordinates. In cylindrical coordinates, we only have one triple integral. In spherical coordinates, it turns out we're going to have a sum of two triple integrals. But we're asked to integrate with respect to rho, then phi, then theta. And the first integral, in the first integral, all variables start with 0 and they go to some functions or constant on the outside. And then over here, we're told with the second integral, our phi value actually starts at arctangent of 1/7 and goes to some other value. So we're going to need to think through all of that. And then we're supposed to evaluate the simpler of the two integrals or sums of integrals. I think we can probably tell that evaluating this one integral is going to be simpler than evaluating both of those and adding them. So we will evaluate this one and then we're going to get an answer. So that's what they're looking for. The way you want to start this is you want to look at this triple integral that's given to you and then state the appropriate bounds for z, for y, and for x by using that relationship that I just outlined earlier, and then use that to graph the solid region that we're interested in. So we're told that z starts at x squared plus y squared and goes to 49. And our bounds for y are the negative square root of 49 minus x squared and the positive square root of 49 minus x squared. And the bounds for x are given as -7 and 7. Okay, so remember with your bounds for z, you want to think of this as going from a bottom function to a top function. So I'll graph one function at a time, or one surface at a time. Z equals x squared plus y squared is an elliptic paraboloid facing up with its vertex at the origin. So we're going to see something that looks like this. And then z equals 49, that's just a plane up 49 units from the xy plane. So it's going to intersect something like that. Okay. Now these two sets of bounds for x and y are going to give us the part of this solid region, the region between this surface and that surface that we're interested in. We want to think of this as describing the projection of that solid onto the xy plane. Now, if I was just given these two bounds and I wanted the projection of the solid, I would take the equation of this circle and then I would project it down and then I would get something. But that's not what we're doing here. We're not using this to infer that region. We're using this to infer the region. So I'm going to start graphing in the xy plane. Hopefully you already recognize the equations. It's okay if you don't. but we've got y equals a positive square root of 49 minus x squared, and y equals the negative square root of 49 minus x squared. So we've got y equals plus or minus the square root of 49 minus x squared. To get rid of the radical, we can square both sides. That gives us y squared equals 49 minus x squared, and if we add x squared to both sides, we get x squared plus y squared equals 49. That's a circle of radius 7 centered at the origin. And y goes from this negative square root, that's the bottom half of the circle, to the positive square root, that's the top half of the circle. So y goes from here to here, while x goes from negative 7 to 7. So that gives us the whole circle. I think we can see why this would be easily described in cylindrical coordinates, because that region, that projection onto the xy plane, is easy to describe in polar coordinates. Okay, now let's think about the relationship between this circle and this equation and this image here. I've got z equals x squared plus y squared on this surface, and z equals 49 on this surface. So those are going to meet on the circle, x squared plus y squared equals 49, just up 49 units. So it's exactly the same circle that we have here. So it turns out the region that we're integrating over is the entire solid region between this elliptic paraboloid and that plane. It looks something like that. So if somebody just said, find the volume between this surface and this surface, the projection would be this. So that's the region that we're integrating over. Okay, and now after we've graphed our region, the next thing we want to do is use our graph to come up with appropriate bounds for cylindrical coordinates. But just quickly, I want to outline what we're going to do for both of these. You want to come up with the appropriate bounds for that region in the appropriate coordinate system. You want to take the old integrand and write it in the new coordinate system. And you want to take your dv and write it in the new coordinate system, and then you're going to substitute. So we need bounds, we need an integrand, and we need a new dv. And that's all we're doing. So let's look at this picture and use the picture to come up with appropriate bounds for this in cylindrical coordinates. So I think we can see in the xy plane that r goes from 0 to 7. Because remember, r equals 0 is just the origin, r equals 1 is a circle of radius 1, r equals 2 is a circle of radius 2, and so on. So if I want a solid disk, a disk of radius 7, r goes all the way from 0 out to 7. Now, if I want the whole disk, I don't just want part of it, I don't want just a semicircle or a quarter of a circle, but I want the whole thing, well, that's when theta comes into play. Theta is an angle that sweeps around the xy plane. So theta starts over here, and I'm thinking of it as an angle that sweeps. So it goes from there, and it sweeps all the way around, and it's back there. Or I can draw it this way. So theta starts at 0 and ends at 2 pi. So those are our bounds for r and theta. And in cylindrical coordinates, z just stays z. And x squared plus y squared is r squared. And z equals 49 stays z equals 49. So these are our bounds. After stating your bounds in cylindrical coordinates, you need your integrand in cylindrical coordinates. The original integrand, let's write that down, was just x. In cylindrical coordinates, x is equal to r cosine theta. It's the same identity that we use in polar coordinates. And then the last thing we need after we get appropriate bounds, a new integrand, and a new integrand is a new dv. In rectangular coordinates, dv is dx, dy, dz. And of course, you can change the order if you want to. In cylindrical coordinates, dv is r times dv dr d theta, and of course you can change the order if you want to as well. So our original integral, let's make it as generic as possible, was just the triple integral over the region Q of x times dv. Now I want to describe the region Q in cylindrical coordinates. So z goes from r squared to 49, and r goes from 0 to 7, and theta goes from 0 to 2 pi. So we've got our new bounds. And then we need x in cylindrical coordinates. That was r cosine of theta, so you substitute that in. It's your original integrand. And then you need a new dv. In cylindrical coordinates, remember it's not just dz, dr, d theta, it's r times that. Oops. dz, dr, d theta, and that's appropriate given the way I ordered these bounds. These are z bounds, then r bounds, and then theta bounds. All of this is the new dv. When you're entering this in WebAssign, they're not going to ask you for this original integrand times r, they want the new integrand. So you kind of have to put these two pieces together to get the new integrand. The new integrand is r times r cosine of theta. So we get r squared cosine of theta. Okay, so I would go up here and I would type that in, r squared cosine theta. Z goes from r squared to 49, r goes from 0 to 7, and theta goes from 0 to 2 pi. And that is the integral in cylindrical coordinates. It's actually pretty easy to evaluate, and we'll probably evaluate that later. Now let's talk about describing the same region in spherical coordinates. We go through basically the same process. I just need Q in spherical coordinates, my integrand in spherical coordinates, and my dv in spherical coordinates. It's a little bit more complicated in spherical coordinates. That's why we have to add two triple integrals together. So let's think about how that would work. Now, in order to see that this is going to be the sum of two integrals rather than just a single triple integral in spherical coordinates, it's helpful to remember what phi equal to a constant value represents. If phi equals a constant, and that constant is between 0 and pi over 2. What you get is a cone. So let's say it was pi over 4. Phi equals pi over 4 looks like this. We go pi over 4 units, or radians, out from that z-axis, and then you let theta range to take on all values, and you let rho range to take on all values. So this is actually an infinite cone. It goes on forever this way. So that's what you would get. With that in mind, I think you can see that we're going to have two ranges of values for phi. One range of values is inside this cone. So phi is going to start at 0, and it's going to end on that cone right there. And then there's another range of phi values that start on the cone and end at the elliptic paraboloid. That's going to be our second integral. So keep all of that in mind. And remember, when we looked at the projection onto the xy plane, it was just a circle of radius 7. centered at the origin. Okay, so keep all of that in mind. Now, first thing we need are bounds in terms of spherical coordinates. The way I like to start in spherical coordinates is I like to take the equations of the solids that we were given, or not solids, the surfaces that we were given. This is z equals 49, and then this was z equals x squared plus y squared. Each of those needs to be represented in spherical coordinates. So I'll start with z equals 49. Remember, in spherical coordinates, z equals rho times cosine of phi. And we're going to want bounds for rho. So we'll get rho by itself by dividing both sides by cosine. And 1 over cosine is secant. So we get 49 times secant of phi. So rho is going to start at 0 because rho equals 0 is at the origin, and it's going to go out to this plane, at least while phi is in this range between 0 and whatever that is. So for our first integral, rho is going to start at 0 and it's going to go to the plane. And the plane is given by this 49 times secant of phi. Okay, now to take on, or to figure out the bounds for phi in the interior of this cone, we need to take a closer look at this triangle right here. Now it looks like it might be difficult, but it's actually not too bad at all. This is a circle of radius 7 right here. So if we are in the YZ plane, this is x equals 0, y equals 7, z equals 49. So back in the YZ plane, what you're seeing with that cone is something that looks like this. Actually, maybe I shouldn't have labeled that as 49. This is 49 units in the z direction because we're going up 49. And then at the same time, we're over here at 0, 7, 49. This is 7 units. And that's our angle phi. If you're saying to yourself, what on earth? Just remember, we're in the YZ plane. Maybe that line doesn't really help very much. We're in the YZ plane, and this is x equals 0, y equals 7, z equals 49. And this point is x equals 0, y equals 0, z equals 49. Okay, so I can just use a trig function to identify phi. I've got the side opposite phi and the side adjacent to phi. So it makes the most sense to use tangent. From this picture, we know that tangent of phi is opposite over adjacent. That's from right triangle trig. Opposite side is 7 units long and the adjacent side is 49 units long. So we just get 1/7. Oops, it's not a theta, it's supposed to be a phi. We should have phi equals the arctangent of 1/7. To get rid of the tangent, we take the arctangent of both sides. And so we get that. Now phi starts at 0 and it goes to that cone. So phi is going from 0 to the arctangent of 1/7. And we want the whole cone. We go all the way around because our region R in the xy plane looks like this. So theta goes from 0 to 2 pi just from that picture. Okay, so I'm going to put these in boxes just for right now. Got this part, and this last part. keep those in mind. We might need them later, or we're going to need them later, excuse me. Okay, so that's just for that cone that's inside that elliptic paraboloid. Now I'm interested in going from the cone to this surface here, z equals x squared plus y squared. So let's convert z equals x squared plus y squared to spherical coordinates. Z is rho cosine of phi. X, ooh, I don't know if I'm gonna have enough room for this. X has quite a long expression and so does y, so I would substitute both of those in and simplify. I don't think I have enough room, excuse me. So I'll just do that down here. Remember how this works? You want to square each factor separately when you're squaring a quantity like that. Then you want to look at this term and this term, and you say to yourself, what do they have in common? Well, they have that rho squared sine squared phi in common, so you can factor that out. And then you say to yourself, rho squared sine squared phi times what? Gives you the first term. We're missing the cosine squared. And this times what gives you the second term. We're missing the sine squared. And if you distribute, you get this back. So you know you've done it right. Now, sine squared plus cosine squared, if they have the same angle, is 1. So that's exciting. And now we've got this equation. Rho cosine of phi equals rho squared sine squared phi. And I want to get rho by itself. So rather than dividing both sides by cosine of phi and having a rho on this side and a rho squared on this side, I'm going to divide both sides by, let's see. I want to have a single rho on this side, so I'm going to divide by rho sine squared phi on both sides. That gets rid of one of the rows, that gets rid of the sines. These rows reduce, and so you have rho equals, you got cosine over sine, squared, excuse me. And you can factor that. That's 1 over sine of phi times cosine of phi over sine of phi. And you remember from your reciprocal identities from trig, 1 over sine, excuse me, is cosecant of phi, and cosine over sine is cotangent of phi. So that is one of our boundaries for rho. Now rho is starting at 0, and it's going out to this surface when phi goes from this value to that value. Okay, so rho for the second integral is going to go from 0 to cosecant of phi, cotangent of phi. Now the bounds for phi are a little bit more challenging. Fortunately, we know where we start. On this cone, phi is equal to arc tangent of 1/7. If you're saying to yourself, how on earth can I figure out what phi equals here if converting z equals x squared plus y squared didn't lead to an equation for phi? It didn't tell me that phi is equal to a constant. It told me that rho is equal to this function of phi. Yes, I completely understand that. That was my first question too. But now let's think about it. This surface, z equals x squared plus y squared, is tangent to the xy plane. So even though right here it doesn't look like phi is going from arctangent of 1/7 to pi over 2, if we get really close down here at the bottom, that angle is getting very close to pi over 2, so infinitely close. So the upper bound for phi is pi over 2 because the smallest or actually the largest value of phi, the largest distance from that z-axis to the xy plane is going to be the entire 90 degrees, or pi over 2 radians. And we want the entire thing, it goes all the way around the xy plane, so theta goes from 0 to 2 pi. Okay. So we've got two integrals. And we're starting with this integral here. We're taking the triple integral of x over the solid region Q, and it's going to be the sum of two integrals. For our first integral, rho goes from 0 to 49 secant of phi. And if you're wondering to yourself, what was that again? That's rho going from 0 out to that plane, z equals 49. Phi went from 0 to the arctangent of 1/7. And that came from this triangle that I've just drawn. It's so ugly. It looks like that right there. A tangent of phi is 7 over 49. So we get this, and we solve for phi, and we get arctan of 1/7. And then theta goes from 0 to 2 pi. Okay, so we've got bounds in the new coordinate system. Now we want the original integrand in spherical coordinates. Well, in spherical coordinates, x is equal to rho times sine of phi times cosine of theta. So we've got the original integrand in spherical coordinates, and then dv can be written in spherical coordinates as well. It's rho squared sine of phi times d rho times d phi times d theta. And I'm using this order because of the order that we listed them here. I'm also using this order because it's the order that they suggested on WebAssign. So we needed to substitute in that dv as well. Now, when you enter your answer on WebAssign, they don't want it in this factored form like this. You've got your bounds, you've got your integrand, and then you've got your dv. But the new integrand comes from taking that extra factor, that rho squared sine of phi from the dv, and multiplying it by the original integrand. So the new integrand is rho times rho squared is rho cubed. Sine times sine is sine squared phi times cosine of theta. And this is going to be exactly the same for that second integrand, or that second integral, excuse me. Because remember, we are taking the triple integral of x over this region, and we split this region into two parts. We split the region into the part where phi goes from 0 to arctangent of 1/7, and rho goes from 0 to the equation of this plane, which is 49 secant of phi. And then we said phi also goes from arctangent of 1/7 to pi over 2, while rho goes from 0 to the equation of this surface in spherical coordinates, which was a cosecant of phi times cotangent of phi. So that's why we had to do two integrals. But this part will stay exactly the same. The second part they still want d rho, d phi, d theta. Theta went from 0 to 2 pi. That was easy. Phi went from arctangent of 1/7 to pi over 2 because it was tangent to that xy plane. And rho went from 0 to the spherical equivalent of that elliptic paraboloid equation, which turned out to be rho equals cosecant of phi times cotangent of phi. Okay, so that is our triple integral in spherical coordinates, and it actually ends up being the sum of two triple integrals. Personally, I would rather not evaluate this. If I have to choose between this and this guy from earlier, I think I'll evaluate this guy, but we know that they're equivalent to each other. These are all equal to each other, so we'll get the same answer. So I'm going to focus on this now and figure out what the triple integral of x is over the region Q. Remember how this works. We start on the inside and we work our way out. First, anti-differentiate with respect to z. That's constant with respect to z. This should be a 7, sorry. The antiderivative of a constant with respect to z is that constant times z, evaluated from z equals r squared to z equals 49. When I substitute in 49 and r squared and subtract, I get 49 minus r squared. Just going to write that here next to the r squared. Now I've got r squared times another function of r squared. So in order to integrate this with respect to r next, it makes sense to distribute that r squared in. Cosine of theta is constant with respect to r, so you can factor that out. Factor it out of the r integral, but not the theta integral. And we'll distribute the r squared here. And then we evaluate this. Bring the 49 down, and then we use the power rule. Add 1 to the exponent and divide by the new exponent. Bring the negative 1 down. Add 1 to the exponent and divide by the new exponent. Evaluate at r equals 0 and r equals 7 and subtract. So I've got 49 times 7 cubed over 3 minus 7 to the 5th over 5. And then when we evaluate this at r equals 0, we just get 0. So it looks like I've got 7 to the 5th over 3 minus 7 to the 5th over 5. 7 to the 5th, 1/3 minus 1/5, that's 5/15 minus 3/15, so 2/15. We're integrating cosine of theta now from 0 to 2 pi. Antiderivative of cosine is sine. We substitute in 0 and 2 pi and subtract. Are you kidding me? You see why I said, are you kidding me? Factor out the constant. Sine of 2 pi is 0. Sine of 0 is 0. And so it turns out that the triple integral of x over the solid region Q is 0. A little bit anticlimactic, but that's the way it goes sometimes.